Hello guys, good morning. Good morning to all of you. Can you hear me? Today we'll be discussing the second part of vector atom model in Stern-Gerlach experiment. On the last class, we could not continue much. Experiment. On the last, I hope everything is all right, so we can start today's session. And how are you guys? Nowadays, people are getting affected with cold. I'm also one of them, but it's okay. It's a part of life. We have to suffer, we have to enjoy, and that makes the life. Good morning, Ajay. Okay, so before I start, let me tell you about the next Sunday test question. So the next Sunday test will be based on two subjects. One is mathematical methods of physics. Another one is classical mechanics. So if you include more and more syllabus, so then effectively you can revise. So for tomorrow's test, you can revise mathematical methods and classical mechanics. You can just revise all the formulae, whatever formula we have. Then some good questions you can attempt. Look, in the Sunday test, we are giving you only 15 questions. For 15 questions, we are giving you 1 hour, 15 minutes. So that is quite sufficient time to attempt new questions. In your real exam also, in part B, you will attempt, let's say, 12 to 15 questions. You will try to attempt, you have to attempt 12 to 15 questions in part B out of maybe 25 questions. Here we are not giving you option. Here we are giving you exact 15 questions and you have to solve them all. So in this 15 question, if you can even solve 7 to 8 questions, that is more than sufficient. Okay, I am keeping a pass mark of 35%. Okay, so mathematical methods and classical mechanics, these two are the syllabus for the next Sunday test. Good morning, Muli. Now let us start our discussion with this particular topic, but my pen is not working as usual. It started working. So what will happen if you keep an atom? Now, atom means you have electron. Electron is revolving around the nucleus and that behaves like a dipole. So it is like behavior of a dipole in a magnetic field. Behavior of magnetic dipoles in external magnetic field. External magnetic field. And also we will discuss the concept of Larmor precision. This particular lecture is very important, guys. Questions may come from this. Okay, so you just consider this let's say we have an electron which is revolving around the nucleus. Okay, this is, let's say, the electron which is revolving around the nucleus in this way. So this is circular. Actually, we have shown you in different perspective. That is why it is looking elliptical, but it is circular in nature. Okay, so this will behave, this whole loop will behave like a magnetic dipole, and you know the magnetic dipole moment will be given by I, current flowing through the loop into A, area of the loop. Okay, so you can imagine it in this way. Now if you place this loop, or you can say this atom, in an external magnetic field, let's say a magnetic field has been applied along the z direction. So this is the direction of the magnetic field. This is the magnetic field direction is denoted by B. So what will happen under this situation? This orbit, this electron orbit will precess around the magnetic field. So if I show you how it will precess, you see this orbit will precess. It will be maybe it can take different shape. If you have seen some animation, how atoms behaves. Now the magnetic field, sorry, the orbital angular momentum will act in a perpendicular direction to this orbit, okay, to this plane of this orbit. So if I imagine that this is the direction of the orbital magnetic moment, okay, because if an electron is revolving around the nucleus in a circular trajectory, its angular momentum is given in this way, okay, every time perpendicular. Now you imagine that the electron orbit becomes like this. Then what will be the direction of the orbital magnetic moment, orbital angular momentum? It will be in the perpendicular direction. Now you imagine it is in this way, maybe in this direction. So because of this precision, it will make a cone, right? It will make a cone. The tip of the angular momentum vector will make a cone like this because of the precision of the electron orbit. So I have just shown you one direction of the angular momentum, so it will create a cone like this. So this precision is called the Larmor precision. Okay, so let me just give a brief writing about this Larmor precision. An electron moving around and you have seen that it is moving in the counterclockwise direction, moving around the nucleus of an atom is assumed is equivalent, assumed we can also write, an electron moving around the nucleus of an atom is equivalent to a magnetic dipole. That we already discussed in the last lecture also. Dipole. Hence, the way magnetic dipole behaves, it will also behave. And when the atom is placed in a placed in an external magnetic field, the electron orbit it is not talking about the electron, it is talking about the electron orbit precess electron orbit. So third person singular number. So precess, this is the main verb. So precesses. Okay, the electron orbit precesses about the field. The electron orbit precesses about the field. About the field direction as axis. And as you can see it in this figure, this precision is called Larmor precision. This precision is called Larmor precision. And the frequency with which this Larmor precision is happening is known as the Larmor frequency. and the frequency of this precession is known as Larmor frequency. So, in this figure, what we have shown? We have shown that an electron is revolving around the nucleus, okay, and the corresponding angular momentum vector, it is making a cone in the direction of the magnetic field, okay. So, orbital angular momentum vector L is represented as a perpendicular vector to this electron orbit, plane of the orbit, okay. So, you can just write this thing here in this figure. An electron orbit is shown in an external magnetic field. External magnetic field, the orbital angular momentum L of the electron is, we need to keep some space to further draw here. So, keep the space reserved for the drawing. The orbital angular momentum of the electron is perpendicular to the plane of the orbit. And let us say this angular momentum is making an angle of theta with the magnetic field direction. So, this angle is theta, let us say. Let theta be the angle between L and B. So, in this scenario, what will be the orbital angular momentum of the electron? The orbital angular momentum is L, orbital magnetic dipole moment, not the spin, it is orbital magnetic dipole moment. We have already derived that. What is the orbital magnetic dipole moment? Mu, let us say L of the electron, we have derived it on the last class. Mu L is equals to minus E by 2m times L. If you write in terms of Bohr magnetron, E h cut by 2m by into L by h cut. So, for the timing we are writing it in this way. This is the orbital magnetic dipole moment, and as you can see, the direction of mu L is opposite to the direction of L because of the negative sign. So, in which direction mu L will be pointing? It will be the angle between mu L and L is 180 degree. So, if L is this direction, so mu L will be exactly in the opposite direction. So, if you want to show the direction of, let us say, mu L, it will be somewhere in this direction, right. Now, if L is making a cone, this mu L will also make a cone, right. This mu L will also make a cone in the field direction. This is the direction of mu L. And what will be this angle? This angle will again be theta. To make a better visualization, we can also add few things. Like this. Okay, so are you getting these things? If you have any question or confusion at any point, you can let me know. So this is the orbital magnetic dipole moment. So as a result of the interaction with the magnetic field B, the dipole experiences what a dipole experience if it is kept in a magnetic field. Dipole will be experiencing torque, isn't it? Because F is equals to E into E. Let's say for magnetic field the expression will be different, but F plus and F minus will be acting and they are in opposite direction, so it will create a torque. So as a result of the interaction with the magnetic field B, the dipole experiences a torque, let's say tau. What is the expression of tau? We have already read about this. Tau is equals to mu cross B. We will write mu L cross B. This is the formula of torque for a magnetic dipole placed in a magnetic field. Okay. Now you see, what will be the direction of the torque? It is the cross product of mu L and B. So it will be in a direction which will be perpendicular to both mu L and B. Okay. Thus, the torque from the property of the cross product, right? The torque tau is acting on the plane, acting on the dipole is always perpendicular to the angular momentum. If it is perpendicular to mu L, it will also be perpendicular to angular momentum L. Okay. So that will let's say take this one along this direction because of the torque applying on this orbital magnetic moment. Okay. Sorry, the torque acting on this orbital angular momentum, because of this a perpendicular in a perpendicular direction this will be displaced. Okay. So let's say this displacement is dl. Okay. Now if this is theta, now if you add this, so previously here it was, now it will be here. Try to understand what we are doing. What does the torque do? So we know that the torque causes the angular momentum, torque causes the angular momentum to change according to torque. Tau is equals to rate of change of angular momentum, so dl by dt. Okay, and this change takes place in the direction of the torque. From this above relation, you can see direction of tau is same as it is rate of change of angular momentum, but the direction of tau is direction of L. So torque is applying in the perpendicular direction. So change in L will also happen in the same direction. So that is why change in L dl is happening along this direction. Okay. So you see, if this angle is theta, what will be this perpendicular? This will be your L sin theta. This portion will be your L sin theta because of this theta. Now let's say this theta amount it changed. You do not know how much it changed. We know the rate dl by dt. If this the frequency is omega and if it takes dt time, then this angle will be omega times dt. Okay, omega is equals to d theta by dt. So what is d theta? D theta is equals to omega by dt. This one we have got, we just remember this formula, that omega is equals to d theta by dt, rate of change of angle with time. So in dt time, how much is the change in angle? D theta is equals to omega times dt. So that is why this angle is omega dt. Therefore, the torque produces a change in L dl in time dt. Now you see, each time the angular momentum is changing its direction, but the magnitude of angular momentum is remaining same. Wherever you consider on the cone, the magnitude means this length of L, it is remaining same, but each time the direction of the L is changing, okay, in this way. So what we can say, that the angular momentum is remaining constant with its magnitude, but its direction is continuously changing. Okay. The angular momentum remains constant in magnitude but its direction changes. Okay. Now as time goes on, the vector L traces a cone around the magnetic field direction, around the field direction B such that around the field B, we should not write, around the field B such that the angle between L and B remains constant. You can see clearly from this image that the angle is remaining theta in this cone. Whatever cone is making, angle is always theta, right? Now you see, this is the precision of L, and precision of L directly means precision of the electron orbit, because L is always the perpendicular to the electron orbit. If L is changing, obviously the electron orbit will also change, maybe here, now here, 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 here. Okay, this is the precision of L and hence of the electron orbit around B. Is this concept getting clear? This is a very crucial concept. Now let's do some mathematics for this. So let's say if omega is the angular velocity, if omega be the angular velocity of precision then L precesses through an angle, let's say omega dt in time dt, that I have already explained. So what will be the value of omega dt? You see, if you have something like this, if you have an arc in this form, so if this angle is making, this is the angle made by this arc, let's say we can say this radius is r and this is the arc, let's name it by S, let's say. So angle is equals to arc by radius. Angle is equals to arc by radius. So we can say that theta is equals to S by r. So here theta is equals to omega dt, and this S which you have here, S is equals to dl here. Okay, so omega dt is equals to dl divided by, and what about this r? R is L sin theta, as you can see in this figure. This is theta, this is L, so this is L sin theta. L sin theta is constant like the radius. So dl by L sin theta. So from this, omega is equals to dl by dt, let's keep it together, into 1 by L sin theta. dl by dt we know already, torque. So torque by L sin theta. Now we know torque tau is equals to mu L cross B, right? So mu L cross B is equals to mu L into B sin theta, right? Torque is equals to mu L into B sin theta. So what will be the value of omega? Let's put the value of omega mu L into B sin theta. So sin theta is getting cancelled. So mu L into B divided by L. And what is this omega? This is the velocity with which the precision is happening. So this is your Larmor frequency. Okay, this is the not Larmor frequency. You see, thus the angular velocity of Larmor precision. So velocity corresponding to the angular velocity corresponding to the Larmor precision is equal to the product of the magnitude of the magnetic field, B, and the ratio of what is mu L? This is orbital magnetic dipole moment. Ratio of the magnitude of the magnetic dipole moment to the magnitude of angular momentum. Okay. Now you already know this. You already know what is the value of mu L by L. We have seen that mu L by L. Mu L is equals to minus E by 2m into L. So if you only consider the magnitude, so mu L is equals to E by 2m into L. So mu L by L is equals to E by 2m. We can write, and from that we get the value of omega is equals to EB by 2m. This is the Larmor frequency. Larmor frequency in this in terms of omega, in terms of f. If you want to calculate, then you have to divide by 2 pi. Okay. So this formula is very important. This is also one expression of the Larmor frequency in terms of omega. Now, what is the Larmor frequency? The Larmor frequency, that is the frequency of precision, is therefore f is equals to omega upon 2 pi. Omega is equals to 2 pi f from that formula. So 4 pi m EB by 4 pi m. So in your question, whatever whatever quantity you are asked to calculate, you will calculate accordingly. Now you can see there is no term like theta here. It is depending only on the magnetic field. Electronic charge is a constant, mass of the electron is also constant, 4 pi is constant. So it is wholly dependent on the strength of the magnetic field. Okay, so it is independent of the orientation angle theta between orbit normal. What is orbit normal? Orbit normal is L to the field direction B. Clear? Now, if you understand this derivation, then the next thing will be very easy for you. Is there any question till now? Tell me if anyone has any question till now. Now, if I want to make it simplified, you can imagine it in this way. Consider a CD. CD you have seen, circular disc CD. You imagine a CD, and at the central point a rod is attached rigidly. Okay, CD and a rod is attached. That direction of the rod is showing the direction of the angular momentum. Now, if this angular momentum changes, obviously the CD will be changing accordingly, because it is rigidly attached. So, the way the rod is revolving, the CD will also show precision, that is the Larmor precision. Now, you see, you can imagine it in this way, CD and the rod. Now, if this L is changing, it can also change theta, it can take different values of theta. That thing is given in the space quantization. Let us talk about space quantization. For a particular, you see, for a particular value of L, what may be the possible components of Lz, that is given in the space quantization. Let us talk about space quantization. Space quantization. So, we have this familiar picture. We have this familiar picture. Let us draw it little big. This is the electron orbit, and let us say a magnetic field has been applied along this direction. Its orbital angular momentum will have a direction like this. Okay. So, this is the direction of magnetic field B, this is the direction of L, and this angle is theta. And the component of L in the field direction, what will be that? If I talk about the component of L in the field direction, it will be something like this. So, let us name this component. What is this component? You already know, that is Lz. If you imagine that the magnetic field has been applied along the z direction. Here an electron is revolving. This is the electron orbit. If I consider that if the magnetic field B is along the z direction, this direction is the z cap direction, then the component of L parallel to the magnetic field, what will be that? will be Lz. That is, you can see from this figure, it is L cos theta. So from this we get the value of cos theta, that is Lz by. Now, as per quantum mechanics, what do you know? The magnitude of L and Lz, they are quantized. So quantum mechanically, the magnitude, we have discussed this while discussing the angular momentum chapter in quantum mechanics. Quantum mechanically, the magnitude of the angular momentum L and its component Lz, let's say, and its z component Lz are quantized, means they can take discrete values according to the relations. You know the relations. What are the relations? The magnitude of L is equals to, this is the orbital angular momentum L. This is equals to root over L into L plus 1. This capital L is the orbital angular momentum. Small l is the orbital quantum number. Okay. Into h by 2 pi or h cut. And what about Lz? Lz equals to ml, it's a magnetic quantum number, and this is the z component of L, Lz, ml h cut, so h by 2 pi. These two are the quantized relations of for L and Lz, where L and ml are orbital and magnetic quantum numbers, magnetic quantum numbers respectively. Okay, so if I put these values here in the expression of cos theta, what you get? Cos theta is equals to Lz by L. So obviously we are getting ml by root over L into L plus 1, h by 2 pi is cancelling. Now, you know, for a given L, how many orientations, how many values of ml are there? Now, ml can take values between minus L to plus L, you know it already. So, for a given L, there are how many possible values? Minus L to plus L, 12, and with 0 it is 12 plus 1. There are 12 plus 1 possible values of ml, right? So how many theta values it can take? Look, if you keep only one value of L, ml values will be 12 plus 1. So how many theta values will be there? Thus, theta can assume, it can also assume 12 plus 1 discrete values, right? For a particular value of L, cos theta can have 12 plus 1 discrete values, means theta can have 12 plus 1 discrete values, and hence we can say that L can have 12 plus 1 discrete orientations in space with respect to B. Okay. This is the quantization of angular momentum, space quantization. This is known as space quantization. This quantization of orientation of electronic orbit. It is not like this. What is this? Kya gaya yaar? Okay, this quantization of orientation of electronic orbits in space is called space quantization. You understood the meaning of quantization? Quantization means it will involve discrete values. Now, the possible orientation of L is 12 plus 1, that is discrete. That is why this is called space quantization. So, if I write for a given value of L, what are the values of ML for a given L? What are the values of ML? ML may be minus L plus 1, minus L plus 2, so on, it will keep on increasing 0, then 1, 2, 3, 4 and up to plus L. Okay. If you want to write another term, you can write it in this way, that the second last term is L minus 1, then L. Here we have written 3 terms, so let us write here also 3 terms. Now, as you can see, root over L into L plus 1, will it be greater than ML or less than ML? Can you tell me? Will it be greater than ML or less than ML? Which one? Tell me. This has a very important consequence. Root over L into L plus 1, it should be greater than or less than. Harry, Murli, Ajay. Look, ML can maximum take minus L to plus L. So, magnitude wise, the maximum value of ML is small l. So, root over L into L plus 1, will it be greater than or less than ML? Less than. How less than? Take any example, minus 2 to plus 2, let us say. So, ML can take maximum value 2. Maximum value of ML is 2. Root over 2 into 2 plus 1 is less than 2. Think little bit. It is like square root. So, L and L square, then the root will come L. Now, if you have L plus 1, so obviously it will come greater than L, and the maximum value of ML is L. So, this will not be greater. Getting my point or not? Harry? It will be greater, na? So, this has a very important consequence. So, we know cos theta is equals to ML by root over L into L plus 1, and root over L into L plus 1 is always greater than ml. So that directly means ml by root over L into L plus 1. What will be the value? It will be less than 1. So we can say that cos theta is always less than 1. Okay. So that is cos theta is not equals to 1. It means theta not equals to 0. What is the meaning of theta is equals to 0? If you look at this image, theta is equals to 0 means the direction of L being parallel to the direction of magnetic field P. So as cos theta is not equals to 1 means theta is not equals to 0. It means this L vector cannot orient itself in the direction of magnetic field. Understood? Theta not equals to 0. What is the physical significance of this? That is, L can never be in the direction of B. If I take an example, let's say we consider a particular case of L is equals to 2. Okay. Or let's say if I talk about the magnitude, L is equals to 2. Okay, let's take the orbital quantum number. L is equals to 2. Okay. So what will be the magnitude of L? So it is root over L into L plus 1 h cut. So root over 2 into 2 plus 1 h cut root over 6 h cut. So what will be the value of ml? So one value is 0. So minus 2 to plus 2. So plus minus 2 will come, plus minus 1 is come. So from this we get the value of cos theta, ratio of ml by root over L into L plus 1. So if you take ml is equals to 0, so 0 by something is 0 plus minus 2 by root 6. Root over L into L plus 1 is root 6. So it is plus minus 1 upon root 6. This is plus minus 2 upon root 6, we can say. So graphically, if you want to represent it, how will you represent? Let's say we have this magnetic field direction. Okay. This is your magnetic field direction. The value of L is same, this value is corresponding to L. ml we are getting how many values? 4 and 5. 5 values we are getting. This is your z direction. Okay. So L is remaining constant. So we can imagine it in this way, that if I consider a circle like this, So, how many total values you have? Let us say L is equals to 0. Okay, sorry, ML is equals to 0. So, this is the line. ML is equals to 1, ML is equals to 2. The ML values are in the Z direction, right? Okay, let us first draw this. Try to understand it very carefully. So, these all values corresponding to L, okay, L is equals to root over 6 h cut. So, this is your L, 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 let us say 5 values. So, each time L is equals to same. Okay. And what about the ML values? Or we can also represent it by small l. Small l is equals to 2. So, each value is 2 and ML is equals to, let us say this is 0. Angle is cos theta. Okay. ML is equals to, this is, let us say 1 plus 1. What is the theta value? ML is equals to plus 1. So, you have to consider this angle. ML is equals to 0. So, cos 90. So, this angle. ML is equals to 1. This is the angle theta, right? If you consider ML is equals to 2, this is the angle. ML is equals to minus 1, this angle. ML is equals to minus 2, it is talking about this angle. If you consider these values will be corresponding to ML values. These values will be LZ. You know, LZ is equals to ML h cut. So, this will be your 2 h cut. This will be your h cut. This will be 0. This will be minus h cut. This will be minus 2 h cut. So, these are the values of LZ. Is it clear or not? Now, theta cannot be 0. That is why this L cannot align parallel or anti-parallel to B. Is it clear till now or any question you have? If you are given any question from this, will you be able to handle? So, all we have discussed till now is orbital angular momentum. So, let us talk about the spin also. Electron spin. So, similar treatment will be there, only L will be replaced by S. So, an electron can be looked upon as a charged sphere spinning around its own axis about its own axis, having an intrinsic or built-in angular momentum. If something is rotating, it will have angular momentum, and consequently an intrinsic magnetic dipole moment. No issue in this. So, quantum mechanically also we can get the similar expression. Quantum mechanically, the magnitude of the spin angular momentum S is quantized as per this relation. S is equals to, if we exclude the vector symbol here, S, capital S is the intrinsic magnetic dipole moment, sorry, spin angular momentum. This is equals to root over small s into small s plus 1 h by 2 pi. Is projection of L on the B is called Lz? Yes, Lz is the projection of L on B in that way, or you can say the component of L along the field direction. Capital S is the spin angular momentum, and small s spin quantum number. Now, what is the spin value for an electron? Spin is half, no, fermion. Spin quantum number S is equals to half. So, what will be the capital S value? Root over half into half plus 1. Write it very carefully because these two S are looking same, but they are not same. Root over 3 by 2 h by 2 pi. Now, we can similarly have the component of S along the field direction. The component of S along a magnetic field direction which is parallel to the z direction is Sz. So, this will be corresponding or a magnetic quantum number ms into h by. So, things will be very similar. Okay. If you have understood the orbital one, the spin only just the analogy you have to draw, where ms is the spin magnetic quantum number. Spin magnetic quantum number. And how many values it can take? 2s plus 1 is equals to 2 values. So, s is equals to half. So, 2 into half plus 1 is 2. What are those two values? Plus s and minus s. So, that is, if I talk about ms, the values are plus minus half. Only two values are allowed. For L, there are multiple values corresponding to different L. Here only two possibilities, plus half and minus half. So, we can say that Sz is equals to ms h cut, ms into h by 2 pi, it means plus minus half into h cut. And you know, the way we wrote mu L, here also we can write mu S, the electron's intrinsic magnetic moment. Intrinsic magnetic moment. What is this? Mu S. And you already know that for electron it was minus E by 2m into L. So a Landage factor was multiplied. Here it is minus Gs into E by 2m into S. And you know the value of Gs. The value of Gs is 2. Okay. Here also it is minus, means the direction of mu S and S are opposite to each other. The negative sign indicates that the direction of mu S is opposite to S. So if you summarize things, we can say that, let's say, if I talk about mu L is equals to minus GL into E by 2m into L. So this is equals to minus E by 2m into L. From this we can conclude that the Landage factor for orbital angular momentum, this is L. On the other hand, mu S equals to minus Gs into E by 2m into S. It is equals to minus 2 times E by 2m into S. So Gs is equals to 2. So if I talk about the magnitude of mu S, what is the magnitude of the spin magnetic moment? It will be magnitude of mu S. So if I talk about this, so negative sign is observed because we are taking mod 2 into E by 2m into magnitude of S. So vector S is equals to, you can see this one is the magnitude of S. Actually, this is the magnitude of S. Okay, na? Too much cold I have got. So this will be equals to 2 getting cancelled, E by m. This is root 3 by 2 h by 2 pi. So we can say it is equals to EH by 4 pi m times root 3, and h by 2 pi is this is EH cut by 2m. EH cut by 2m into root 3. EH cut by 2m is equals to mu b. So root 3 mu b. Mu b is equals to EH cut by 2m. So EH by 4 pi. Mu b is the Bohr magnet. So this is the value of this magnitude of spin magnetic moment mu s. It is always root 3 times mu. The magnitude of the spin magnetic moment in terms of the Bohr magneton, it is root 3 times mu. So very important thing actually. Any question till now? So if not, if you do not have any question, you will go for this vector atom model. So a very simple model. Let's write few things before we continue. You know the total angular momentum. So we have seen till now, we have two things. One is the orbital motion and another one is the spin. The total angular momentum. Do you ever imagine how fascinating it is? You look at the solar system. Sun is at the center, heliocentric model, that is called heliocentric model. Sun is at the center and the planet is revolving around the sun in a prograde way. Means the planet is revolving around the sun in a counterclockwise direction. Okay, if you talk about the earth is rotating about the sun in a counterclockwise fashion and it is also spinning around its own axis in the counterclockwise direction. This kind of rotation is called prograde rotation. So that is massive. You can consider sun, planet, earth. So massive, huge thing. Inside an atom, when you come very narrow, inside the atom, electron is revolving around the nucleus in a counterclockwise direction and it is also spinning in the counterclockwise way. So if you think it in this way, it is very fascinating how things are connected. The total angular momentum of an atom results from the combination of orbital and spin angular momentum of its electron. Now angular momentum is vector quantity, so we have to add them vectorially. Since angular momentum is a vector quantity, we can represent the total angular momentum by means of a vector obtained by the addition of orbital and spin angular momentum vectors. As we are doing a vector sum, this model is known as the vector atom model. This leads to the vector atom model of the atom. Now we are considering some atom which has one single electron at the outermost cell. So consider consider an atom whose total angular momentum is provided by a single electron. So, can you give me an example like hydrogen, 1 electron atom, lithium, okay, 2 and 1, sodium 10 plus 1. So, atoms like hydrogen, lithium, sodium, etc. So, they have single electron in the valence shell. So, total angular momentum will be the sum of the total angular momentum of the 1 electron atom is given by J. J is equals to sum of the orbital angular momentum and spin angular momentum. Now, as we have discussed, the way L and S are quantized, J will be quantized in a similar manner. So, like all angular momentum, J is quantized in both magnitude and direction. What is the magnitude of J? The magnitude of J is given by its quantum number. Magnitude of J is equals to J root over J into J plus 1 h cut or h by 2 pi, whatever you want to write, where J is the total angular momentum quantum number. It will be the sum of the quantum numbers of L and S, L plus S or L minus S. So, L plus minus. This J is called inner quantum number. Okay. Okay. So, corresponding to J, there will be JJ also, right? The corresponding Zz of j in the j direction. So, you are trying to observe, you try to observe a pattern. We have done for L first, then S, then its combination L plus S, that is J. Things are pretty similar. Same thing for three different things. Zz is equals to Mz H cut, sorry, Mj H cut. And in the same way, Mj can take the values between minus j to plus j. So, minus j plus 1, so on, 0, 1, 2, j minus 1 plus j. Mj is the magnetic quantum number. Now, if we consider one electron atom, there may be two possible orientations. In one electron atom, if I consider one electron atom, there are only two relative orientations. Only two relative orientations. Which are them? Corresponding to, so it may be either j is equals to L plus S or j is equals to L minus S. So, if j is equals to L plus S, so obviously the magnitude of j will be greater than the magnitude of L. And if you see, j is something which is evaluated by subtracting S from L. So, we can say that for this case, magnitude of j will be less than the magnitude of L, because small l is directly related to capital L. This quantum number, this is angular momentum. The magnitude of capital L and capital J depends on this L and J, small n and small j. Now, what is the meaning of this? J is equals to L plus S, J is equals to L minus S. One example we are taking. What are these two ways? If I take a specific case, the two ways in which L and S can combine to form G. Let us say when L is equals to 1, S is equals to half. So, if I talk about this, this is L, this is your L, this is your S. L, S. So, this will be the direction of J from the vector law of triangular addition. If this is, let us say, L, this is S, L plus S, it is. So, you can see here your J is greater than L. Now, you imagine the opposite case. J is equals to L minus S case. So this is L, S is subtracted from it. So what will be the change in this? So if this is the one direction of S, let's say, what will be the other direction of S? Let's say this is S is equals to plus of, S is equals to minus of, will be along this direction. You can say this is plus S minus S. So this will be your J. This is S, this is J. So this is J is equals to L minus S. So here you can see the modulus of J is less than L. So here we have taken J is equals to L plus S, L equals to 1, S is equals to half. Here J is equals to L minus half, L is equals to 1, S is equals to half. So it is half. Okay, we forgot to draw one picture here. Here we have shown it for L, but we forgot to show it for S. So let's say this is the Z direction. Okay, let's use another color. This is Z. Got it? Now, corresponding to one value of S, there will be how many values of MS? This is your Z curve direction. So one value of Z corresponding to two values of MS, right? So MS can take values plus half and minus half, and the corresponding value of, if I talk about this will be SZ. This is plus H cut by 2 and this is minus H cut by 2. Okay, so that thing has been utilized here, kind of thing. Is it clear, guys? Now a very important thing, let me just draw the figure, then we will explain. L and S, spin angular momentum and orbital angular momentum. This L and S, they are bound internally, that is called spin orbit coupling. S and L, this coupling is the spin orbit coupling. Because of this coupling, we can say an internal magnetic field is developed, and as a result of that, S and L precess about their vector sum J. If there is no magnetic field, external magnetic field present, what will happen? Let's say this is your S, this is your L. So the both will precess about their sum J. This is J, this is S, this is L. So as you can see, L is having a precision about J. S is also having a precision about J. So that is here. So write few lines which are very necessary for you. The angular momentum of the orbiting electrons or the atomic electron S and L, they interact magnetically. The so-called LS coupling, which is because of this coupling, we'll see different kind of effect like Zeeman effect and all, which is known as spin orbit coupling, LS coupling. Spin orbit coupling. And magnetically they are interacting, so they will exert torque. Magnetic, where there is magnetic field, there will be torque. They exert torque on each other. There is no external magnetic field applied. This magnetic field is generated because of the interaction between S and L internally. They exert torque on each other. These internal torques do not change the magnitude of the vectors L and S. That is why they are like making a cone. S is making a cone, L is making a cone. So you can see the length of S and L remaining same, means the magnitude is remaining same, but the direction is not same, because you see it is the tip. You can look at the tip is traversing a cone, so the direction is constantly changing, but the magnitude is remaining same. They exert torque on each other. Because of this torque, the magnitude of the vector do not change, but cause them to precess. So we have already discussed this kind of thing in the first place. Cause them to precess uniformly about their resultant, uniformly around their resultant, है ना? जी. So if the atom is in free space, so that no external torque, no external magnetic field is present, no external torque acts on it, then the angular momentum actually the total angular momentum J remains conserved in magnitude and as well as direction. You can see the direction of J is same. Direction of S and L are constantly varying, but direction of J is same and also the magnitude is same. You can see one line. Total angular momentum J is conserved in magnitude as well as in direction. And because of that, so the angle between L and S would also remain invariant. Do you understand the last line? Do you understand the last line? You can imagine it, J is equals to L plus S. Okay. So angle between L and S is L dot S, you can say. From L dot S we can get the angle, and as J is constant and the magnitude of L and S is also constant, so theta will also remain constant. Have you understood the last line mathematically? Tell me. Is there anyone who could not understand the last line? Murli, Ajay, Hari, could you understand the last line? Okay. So it is very simple. Just let me show you. You can see, to understand the last line, a very simple calculation we need to do. Why it is taking too much? Okay. देखो, we know J is equals to L plus S, right? And J square is L square plus S square plus 2 into L dot S. Can you write? Okay. Or if I want to remove this L dot S, we can write 2ls cos theta. Okay. So from this we can get the value of cos theta, that is J square minus L square minus S square by 2 into Ls. Okay. Sorry guys, just a moment. Yes sir, good morning. Yes, ठीक हो, आप कैसे हैं? बताइए. हाँ हाँ, भेज देता हूँ आपको थोड़ी देर में. बस बढ़िया, बस थोड़ा ठंड लगा है. हाँ हाँ, वो थोड़ा सर्दी लग गया है. हाँ. कौन सा, किस चीज़ का प्रिंट आउट? अच्छा, भेजने को लिए बोला है क्या, या फिर ऐसे ही? जमा कर दीजिए. आई थिंक वो साइन वगैरह भी लगेगा ना. ठीक है, देखता हूँ. हम्म. हम्म. ठीक है सर, मैं देखता हूँ. So you can see what is happening. Okay. So if I just remove this h cut square from all the terms, so the value of cos theta is a constant, right? It will give you a constant value. So theta is equals to constant. Right? Clear? Now this is the scenario when there is no external magnetic field present. What will happen if we apply magnetic field along the z direction? You see what will happen? L and S coupling will be there. So L and S will precess around J and J will itself precess around the magnetic field. So in presence of the magnetic field, what will happen? Murali, understood why theta is constant? In presence of the magnetic field, what will happen? What is happening? Look, L and S, they are coupled together and they are bound to precess around J. But now we have applied the magnetic field B along the Z direction. Okay. We have S, S will precess around J, L will precess around J and J will precess around B. You can imagine it in this way. S is precessing around J. L is also precessing around J and J is precessing around and because of this we get phenomena like anomalous Zeeman effect and all. So the calculation we have done, the same calculation needs to be shown here. What is the value of the angle between L and S? This can be evaluated in this way. Okay. This is the vector atom model. Actually, this calculation we need to do here. Okay, and this is called the vector atom model. It can be extended to many electron atoms also. This is the vector atom model of the one electron atom. Okay, let me give you one problem based on this. Calculate the possible orientations of the total angular momentum vector, let's say J, corresponding to the inner quantum number J is equals to 3/2 with respect to magnetic field along the Z axis. Can I do this? So, the way we have done LZ, similar thing we have to do. So, magnetic field has been applied along the Z cap direction. So, what is same? J is same. J is equals to 3/2 means root over J into J plus 1 H cut means the magnitude of capital J is also constant. Okay. So, how many possible values of mj will be there? Magnitude of the total angular momentum j will be root over j into j plus 1 h cut, right? So, root over 3/2 into 3/2 plus 1 h cut. So, how much is this? Root over 15/2 h cut. What about jz? What about jz? Z is equals to now for j equals to 3/2, mj values will be between minus j to plus j. So, this is minus j 3/2 plus half plus 1. So, half, okay, minus half minus 3/2. Unit difference will be there. And let us say the angle between j and jz. J and jz. So, this is the direction of the magnetic field. So, if I take only one case, let us say this is j. Let us say this is your j is same, its projection on the z axis will be jz, right? Its projection on the z axis will be jz. So, let us say this is corresponding to mj is equals to 3/2. So, jz will be 3/2 h cut. So, this value will be 3/2 h cut. Now, corresponding to different values, let us say this is here we will get half h cut. Here it is minus half h cut. Here it is, let's say, minus 3 by 2 h cut. So the vector j will be oriented in a similar manner accordingly in this way. You can check it. So for all mj values, the j value is same, that is root over 15 by 2 h cut. This magnitude is same. What is changing? Jz is changing. The component of j along z direction is changing. Here it is showing 4 values: 3 by 2 h cut, half h cut, minus half h cut, and minus 3 by 2 h cut. This is corresponding to mj is equals to plus 3 by 2. This is corresponding to mj is equals to half. This is corresponding to mj is equals to minus half. This is corresponding to mj is equals to minus 3 by 2. So what is the angle between j and jz? You see, if you consider mj is equals to 3 by 2, so this is the angle. If you consider the angle between mj, j and jz for this one, so j is equals to half. So this will be the angle. In a similar manner, if you consider this will be the angle. For this one, this will be the angle. Obviously, this angle cos theta, the angle theta between j and the z axis or LZ is determined by cos theta, jz by j, right? So if you imagine it in this way, triangle, so triangle like this, triangle like this, so jz by j, if this angle is theta, jz by j, cos theta. So jz, you know the magnitude, mj h cut, j, you know the magnitude, root over j into j plus 1 h cut. So h cut is getting cancelled. So mj by root over j into j plus 1. So mj root over j into j plus 1 is root over 15 by 2. So it becomes 2 by root over 15 times mj. Now depending on the different values of mj, you will get cos theta and correspondingly you will get the value of theta. So if we consider for mj is equals to 3 by 2 plus half minus half minus 3 by 2, we have cos theta is equals to, you see, 2 by root over 15 into 3 by 2, we will get around 0.775. We will get 0.258. So minus 0.258 minus 0.775. So in this way you can get the value of cos theta. Once you know the cos theta, you can easily calculate the value of theta. So this is how we calculate the possible orientation of the angular momentum vector j corresponding to j is equals to 3 by 2 with respect to the magnetic field along the z direction. Everyone is clear with this? Let me give you one last problem for today. Everyone should be able to do it. The last problem. Just write done if it is done. Too many pages I have kept. Okay, the last problem. In the vector model of angular momentum applied to an atoms, what is the minimum angle in degrees in integer made by the orbital angular momentum vector and the positive z axis for a 2p electron? Tell me. Minimum angle you have to calculate. This is z direction, this is L, this is Lz, this is theta. So you have to calculate the minimum value of theta. L can orient it, L can orient in different theta direction. So what is the minimum value of theta for a 2p electron? Question I think you are understanding. This is the simpler thing. We have done more complicated thing than this previously. Hurry up guys, do it quickly. It should not take much time. You determine all the possible values of theta and just pick up the minimum. Why is it taking too much time? What did I tell you? Cos theta is equals to Lz by L. Option C, very good. Cos theta is equals to Lz by L. Lz means ml h cut. This is root over L into L plus 1 h cut. So this is ml by root over L into L plus 1. Now if I consider a 2p electron, so what is the L value for a 2p electron? sp01 and ml will be between -1 to +1. So the possible values of ml is -1, 0, +1, and accordingly cos theta is equals to root over L into L plus 1 is root over 2. So -1 by root 2, 0, plus 1 by root 2. So corresponding theta values. Look, for 0 we know it is cos 90, 0, 1 by root 2 cos 45, 0. Now -1 by root 2 means you can see all sin, tan, cos. हाँ, ये होता है ना, ये गलत लग दिया मैंने. All sin, tan, cos ये होता है ना. Do you remember? So in the second quadrant, the value of cos is negative. So if it is 40 degree here, so you can add 90 degree, so 135, then it will come to the second quadrant. So this will be 135. Okay. Or it is not adding not adding 90 degree, it is like 180 degree minus 45 degree. Okay. So in that way it is getting 135. So the minimum one is the 45. Is it understood? So with this, let's end the session today. I hope you find this amazing session very useful, and I will recommend you to revise this 2 3 because this is relatively little bit critical concept. Okay? Although things are easy, but if you look at it overall, then things may be confusing. I will not say it is complicated, it may appear to be confusing. So you have to revise it quite a few times so that you don't get confused. Okay. So with this note, let's end the session here. In the next lecture, we'll be covering the Stern-Gerlach experiment. Okay, that will take a little bit of time. So that will continue in the next lecture. Thank you guys. Thank you very much for joining this session. I hope you find this session useful. Bye bye. Take care. Have a great day.